Oxford scientists create rare quantum effect 100 times faster than expected. It demonstrated quad squeezing at a pace that has left the scientific community reeling, achieving the effect 100 times faster than anyone thought possible. For the first time in quantum physics, Oxford researchers have demonstrated quad squeezing, a complex fourth-order quantum interaction. The study introduces a novel method for controlling quantum harmonic oscillators, systems that mimic vibrating objects such as springs or pendulums at the subatomic level. It demonstrated quad squeezing at a pace that has left the scientific community reeling, achieving the effect 100 times faster than anyone thought possible. The result is more than the creation of a new quantum state. It is a demonstration of a new method for engineering interactions that were previously out of reach, said Dr. Oana Basavan, lead author from the Department of Physics, University of Oxford. The fourth-order quad-squeezing interaction was generated more than 100 times faster than expected using conventional approaches. This makes effects that were previously out of reach accessible in practice, Basavan added. The experiment set up physicists have long used a trick called squeezing to sharpen the fuzzy measurements of the subatomic world. It is why gravitational wave detectors, like LIGO, can hear black holes colliding across the universe. But for all its utility, ordinary squeezing is a relatively simple second-order effect. Going higher, into the complex realms of trisqueezing and quad-squeezing, has long been dismissed as an experimental pipe dream, until today. In a recent paper, a team led by Basavan and Dr. Raghavendra Srinivas announced the identification of out-of-reach quantum interactions using a single trapped ion. Two carefully controlled simpler forces were applied to a trapped ion using a phenomenon called non-commutativity. In particular, researchers experimentally demonstrated quad squeezing, a complex fourth-order quantum interaction previously considered too weak to observe. Using a single trapped ion, the team overcame speed limits by layering simple forces to induce a non-commuting effect, generating complex quantum interactions 100 times faster than expected. To explain this, two simple linear forces were applied to a single trapped ion. Then non-commutativity was used to create a quantum interaction exceeding the sum of its parts. Instead of acting independently, the forces influence one another to amplify the ion's motion, thereby tricking the system into generating a much stronger, more complex interaction than either force could achieve alone. In the lab, non-commuting interactions are often seen as a nuisance because they introduce unwanted dynamics. Here we took the opposite approach and used that feature to generate stronger quantum interactions, said Basavan.